Hey kids, it's math time.
Do you want medium black coffee or large black coffee?
This is one of those days. I'll get a large. So today we're gonna go over the gradient operator. The operator itself has properties of a vector, but it typically acts upon a scalar function. So the best way to think about a gradient is that it's its own vector that has and those components are partial x in the x direction, partial y in the y direction, and partial z in the z direction. Well, what does that mean? What does anything mean? I've been awake for 24 hours. So imagine we have a function that takes in parameters x, y, and z. Now I'm going to assign a random expression. Let's say it's e to the x plus y cosine z. If we were to take the gradient of that function, then our I component would be the x partial of the function, our j component would be the y partial. Our I component would be the x partial, our j component would be the y partial, and the k component would be the z partial. If we were to compute this, let's start with our I component. E to the x derived in terms of x is just e to the x. This stuff is a constant, so it stops existing. If we move on to the j component, So if we move on to the j component, we'll be deriving in terms of y. E to the x is a constant, so it stops existing. Now we're worried about y cosine z. Cosine z is a constant.
That's probably gonna have shitty quality since you're filming off your laptop.
Yeah?
It was viewable on YouTube.
It was?
So if we move on to the j component, we'll be deriving in terms of y. E to the x is a constant, so it stops existing. Now we're worried about y cosine z. Cosine z is a constant, it gets multiplied by the derivative of y. Y derived in terms of y is 1. So cosine z times 1 is cosine z. Let's do k now. We're deriving in terms of z. E to the x stops existing, it's a constant. Y is a constant. Now we're worried about cosine z. Derivative of cosine is negative sine. Multiply that by y, so we get negative y. Derivative of cosine is negative sine. We multiply that by our constant y, so we get negative y sine z. That's all in the k direction. So that's how we compute gradient acting on a scalar function. Now there are a couple other computations that take advantage of the gradient vector, and they're all applied to a vector field. One of these computations is called divergence. The other one's called curl. Let's start with the simpler of the two, divergence. Before we do any computations, we're going to get into some visual intuition. We'll do this in 2D, because then it's easier to visualize. So imagine in this space, you had a vector field with vectors at each point going all sorts of directions. If we focus on one point, you could imagine divergence as the amount of the field that is going to that point versus the amount of field going out. Basically, if we were to imagine this as a fluid flow, divergence is going to tell us whether there's more fluid going into this point than there's going out, or vice versa, and the magnitude at which it's doing so. Now that you understand what's going on, let's compute it. So here's the vector field we're going to be using, x squared y in the I component. Oh, no.
I put a ton of effort into mine.
So here's our vector field, x, y in the I direction, cosine z, y in the j direction, e to the x, z in the k direction. Before we do anything else, let's go back to our gradient vector, del x, partial x in the I direction, partial y in the j direction, partial z in the k direction. Blah. I need more caffeine. If you were paying attention like 30 seconds ago, you'll remember that divergence is gradient dot f. Yeah. So we compute that the way we would any other dot product. We multiply all the components and then we add them together. Except this time, instead of multiplying, we're performing the partials on the respective components. So that means del f del x plus del f del y plus del f del z. So now let's compute that. Derive x squared y in terms of x. Boom, 2xy. You already knew that. Derive cosine zy in terms of y. Derivative of cosine is negative sine. Use chain rule to find the derivative inside. You get negative z sine zy. You already knew that. Next partial, e to the x z in terms of z. Derivative of e to a variable power is itself. Derive the term inside that expression using the chain rule. you get x e to the xz. Change this plus minus to just a minus. We fix that z. There are no like terms to add together, so we're done. So let's talk about curl now. Okay, so before we compute, my marker ran out. So before we compute, we're gonna visualize. We're doing all of this in 2D. Let's create another vector field. Let's just make some shit up. Vectors fucking everywhere. So we're gonna pick one point, and the curl is gonna be a vector of its own. It's gonna measure the rotation of this flow field at that point. And on the axis of rotation, if your curl has a positive component, that means the field rotates in a counterclockwise motion. If it's negative, then the opposite happens, and you have a clockwise motion. So on to the computation. Curl is defined as the gradient vector cross-producted with the vector field. We're going to use the same vector field as in last problem. So we have our matrix, we can start computing the cross product. There's our I component, there's our J component, there's our K. We do the derivation, it looks like this. That's it this time. Hope you enjoyed. Hope you learned a lot. Fucking big brain. Next time we'll do surface integrals, I guess.